So, 3 lectures left, including today, which means we finally got to Linux. Almost near the end. Or new Linux, whatever you prefer to call it. I'm going to call it Linux. So this was actually released in 1991, and it's created by someone by the name of Linus Torvalds, which I'm sure many of you would know. Why does it exist? So at the time, Linus wanted a fully functional, free operating system. He was using Minix, and my understanding is that there was nothing available at the time that met his particular needs. So there were other projects that were underway, they were just stalled for various reasons. So Richard Stallman, who's involved with the GNU project, if you want to know why I refuse to call it GNU Linux, it's because I hate saying that word GNU. But anyways. So Richard Stallman's GNU project was actually stalled. And there was no reasonable release date expected yet, so he didn't want to wait around for it. And then there was this thing called 386 BSD, and it was bogged down by legal complications, and so there wasn't really any other options. And so Linus said, hey, maybe I should just make my own, and so he did. And as part of that, he took as much of the GNU project as he could, because it was free, and a bunch of other GPL projects, and he included those as part of it. And the story is, originally it was called this Freaks thing. Now, this story goes, and I don't want to get into trouble for saying this, that he didn't originally call it Linux because he didn't want to name it after himself. That would be very egotistical. I've met the man, and I don't believe that for a minute. He says it was the community that wanted it called Linux. No. Yes, I have met the man. I was at Google. My first week, he came and gave a talk. It was entertaining. He's an interesting fellow, I say that much. That's all I'm willing to say on camera. All right, so you know what Linux is. It's a Unix-like operating system. It's a monolithic kernel, although, of course, there have been some microkernel versions made of it, because it's free and it's open source. So you can take the code and you can do whatever the hell you want with it, except sell it, because GPL and all that. Now, so things that are actually a part of the kernel, that's memory management, virtual memory, IPC, scheduling, file systems, device drivers, all of that, for the most part, is incorporated into the kernel. But one of the things that's not a part of the kernel, which kind of makes it a bit different from some of its the other operating systems, is that X Windows, x386, isn't actually in the kernel. That sits above it. And what's really interesting is because the desktop environment is separated from the actual kernel, you can use whatever desktop environment you want. And if you don't like x386, you can use x11r6. And if you don't like x11r6 and you really like punishment, you can use x11r2 or something like that, where you open up the book and it says, here's how you do X. And then at the very bottom of every single page of the book, it says, actually, please don't do this, it doesn't work. And if you think I'm joking, I wish I wasn't. My very first co-op positions and my very first experiences with Linux involved writing X11 code, and it's a bloody nightmare. I'm glad I don't do that anymore. All right, now, of course, there are also lots of variants of Linux. There are many different distributions, which are both the Linux kernel and slight variations to it, but also software packages and desktop environments. There's way too many for me to name. The first one I ever used was Slackware. Yeah, it was Slackware. And then I moved on to Red Hat very briefly, and I played with Mandrake for a bit, and then Suzy, and then I got tired of the NVIDIA drivers not working, so I broke down and I did a from scratch Gen 2 install where I compiled even the compiler before I compiled the kernel and then everything else, and it took 3 whole days. And that was in 2003, and that was awesome. I don't have time for that anymore, so I use Kubuntu now. But there are many. There's Mint. There's more distros than we can actually name here. And on the topic of, you can change the desktop environment to whatever you want. Well, we'll come back to that. This is Enlightenment in a black and white theme. And if you don't like that, you can go a more Windowsy style with KDE. This is an older KDE. Or you can use TWM if you really like things old-timey. And if you've never seen TWM, go find it and have some fun. That's the environment I grew up with here at the school. Now, what's actually interesting is I want to come back to this little diagram here, and I know you may not be able to see it well, but this is kind of separating the Linux kernel and all of the components into different layers, so you can kind of see how the system is built. So the black at the bottom, that's actually the hardware. And sitting above the hardware, as we would expect, is the actual Linux kernel, which is including things like the Radeon drivers, the NVIDIA drivers. You've got your also for sound, you've got your file systems, you've got all of that stuff, all of the kernel level stuff right there. And that funny little thing over there, that's the fork for Android, because it's of course a fork of the Linux kernel. And then sitting above that, you kind of have the system daemons, the system libraries. That is not a part of the kernel, but it's much closer to it than your user program. So that's things like glibc, that's stuff like your X server, whichever brand you prefer to use. There are some window managers that sit down at this level as well. Not all of them, but some of them. And other various low-level packages. And then on top of that, you've got the user interface libraries, things like GTK, Qt, and so on. Things that if you were to sit down and actually write some code, like a desktop application, you'd be using those. And then on top of those, you actually have the user applications, desktop widgets, and so on and so forth. So there's lots of different layers to this system. And if you're wondering, I've been using, my first experience using Linux was 1996. Playing around with it for a very, very long time. I used to telnet into my friend's machine and just see what I could do with it. And you're like, telnet, what's telnet? That's what we used before we thought security was an issue. By the way, you can still telnet into things. If you're really bored, you can telnet into like the CS Club's mail server and like use it to send mail raw. That's always fun. Or telnet into a DNS machine and start sending DNS queries. There's all kinds of fun stuff you can still do with telnet, even if you can't telnet into regular stuff now. All right, so a couple things to talk about before we get back to talking about file systems. One of them is, hey, you have a final exam coming up. I don't think anybody's cheering. I know there's probably a lot of terror going around because of the high average of the midterm. I respect that. At the same time, we're not total jerks and like, they got so high on the midterm, we better rake them over the coals in the final. I don't do that. I don't have time for that. I really don't. The final exam looks like every other bloody final exam. Because I'm too lazy to change the LaTeX file. In terms of study, there are no practice finals. There's none. So if you're asking for them, I have none to give you. I mean, I'm sure I could give you one from 2003 when I took it, but it would be totally useless. So in terms of studying resources, if you go off the course website where you found all the previous midterms, there's also a bunch of review problems. Those review problems are now your friends for studying for the final exam. The other thing is I also recommend that you go over some more midterms again and go over the midterm solutions as well. The exam is much more heavy to the post-midterm content because for the pre-midterm content, you've had all of your assignments and an exam on it. So you have not been tested in any way, shape, or form on anything that came after. I mean, I suppose you have the quizzes now, but that's not really that much. So it's much, much, much heavier to the post-midterm content. I don't know the split. I don't have time to figure out what it is and what the mark distribution is. You'll find out when you get there. The other thing I want to say is that I'm going to use the last day of class, so Tuesday of next week. That will be a final exam review session. So if you have anything you would like to see again, please do send me an email and I will make sure it's included in the list. There will be slides with extra questions and solutions that will be provided as well, just like for the midterm. So lots of extra stuff. And when you are studying, please, if you have a question about some review problem or some previous midterm problem, please don't say question 7 on exam from F18. Sometimes I answer Piazza Post on my phone and I hate doing it. And I don't know what question 7 on Fall 18 was, and I don't want to look it up on my phone. So if you want to make it easy for us to answer your questions about previous exams or review questions, please post the actual question. That way I don't have to go find it. That would be very helpful. The last thing I want to mention before we move back to file systems is because it is the end of the term, the course evaluation website is up, and we would really appreciate it if you took a few minutes to actually fill out an evaluation. I will give you some time in class probably on Thursday to do that, just at the end. One thing I want to remind you of though is you're filling it out for the person whose section you're actually registered in. So if you're in Allie's section, you're filling it out for Allie. And if you're in my section, you're filling it out for me. And the reason why I want to stress this is because it always ends up when they finally release these to us, which is like a month or two later, I always see, we always get each other's reviews. And it's great if it's a good review. So I get a review from Bernard, and it's like, oh, I love Bernard, he's awesome. I'm like, I'm not Bernard, but I'll take it. But then I get pissed off if I get a message that says, I hate this guy, he's terrible. I'm like, but that's not me. And they don't filter these out because, of course, they're anonymous and stuff. So, yeah, you're filling it out for the person whose section you're registered in. If you don't know what section you are registered in, that's what Quest is for. Maybe, I don't know, I don't log into it very often because I know it's a mess. The other thing is if you do still want to leave feedback, though, RateMyProfessor is also used by the school, and it always has been. Yeah. And it would be nice if we could get lots of people to fill this out, but I'm not going to pressure you. I mean, it was a lot. When I was an undergrad, they kind of forced the issue because we had to fill these out on paper, like little bubble sheets that, fill in. And so they sat it in front of you, and what are you going to do, like not fill it out? I don't know, I love filling out forms, so it's like, oh, you give me a form, I just have to do it. I don't know why, weird compulsion. But yeah, now that it's a web thing, you can like not do it, yeah.
The school uses RateMyProfessor as like an official source of information on their instructors?
I wouldn't say it's official, but they certainly are aware of it and do read it.
So I could like sabotage some random prof's career at some random school by just...
Well, I'm not saying every school does it.
Okay.
But I am saying like, it's certainly something that they are aware of, and it's certainly something that they may use.
Okay.
Yeah, don't sabotage other people.
I'm not.
You're always trying to pull the system down. All right, so then, if you're wondering, by the way, what the school uses those evaluations for, they're for two purposes: to check the health of the course, but also to decide whether someone is allowed to teach again or not. Of course, if they're a tenured professor, it doesn't matter. But that's a long story. I am not a tenured professor. It matters. All right, so let's go back then to not networking. This is the wrong class for that. I don't know, anyone want to learn about data centers today instead? Ah, wait. Take networking in your 4th year. It's a bird course. To be fair, that's what I was told by another professor. It has a reputation as a bird course. Keep it that way. Whatever, I don't... All right. So we left off talking about file systems because obviously on a computer we need to have persistent storage. Otherwise, every time we download a copy of Star Wars, we're going and we put it in RAM and the power goes out because you live at Icon, you're going to lose your copy and you got to download it again. We don't want that. So when we looked at file systems, we noticed there were 3 layers to the file system. You've got the logical file system at the top. That's the API that's provided to you, and that's your entire experience, generally speaking, with a file system. It's providing you with functions like open, close, read, write, functions and programs to modify the metadata of the files, check the size of the files, move files, all of that exists in the logical file system at the top. What's really nice about this is by using this, you don't need to know where that file actually is or how it is being stored. You don't need to know that when you start writing to a file, there's somebody inside your computer, a little tiny dwarf who's like chiseling out the data with a pen, like a chisel and some stone. You don't need to know that. It doesn't matter to you. That would be really slow, obviously. So that's kind of nice. And then below that, we have the virtual file system. And the virtual file system is going to take all of the different physical file systems because on your computer you may actually have multiple at the same time, and it's going to present them to the logical file system as one unified thing so that you don't need to treat writing to your USB device differently from writing to your NAS, differently from writing to this or that. You don't even need to know that. It's all abstracted for you between the virtual file system and the logical file system. Another thing to remember is that every file has a unique number. This unique number is what the operating system and the disk are going to be referring to the file as, not by the name. Strings are slow and really long and, you know, they're a pain. So and they're also not guaranteed to be unique. So inside of the actual system, we are referring to files by a unique number. No 2 files can have the same I number. And then what a directory is, even though we like to think of it as this cute little folder icon that we shove stuff in to call it organized, what it actually is a mapping between a name and an I number. And if you take all those directories, they form this namespace tree, and the path that you have is the path that you take through that tree, mapping each part of the path to an I number to open the next file and find the next I number until you get to the end where you get the I number for the file you actually want. So that's what that actually is. And what's interesting, so we call that mapping between a name and an I number is called a hard link. And you can have as many hard links as you want to a file, but you can only have one hard link to each directory, and that's to prevent cycles. And when there are no hard links left to a file, you can no longer navigate to it. But if there are no hard links to a file, it does not mean it is deleted, because the data could still technically be there. And you'll see kind of why here in a minute. So what I'd like to move on to now is the actual physical file system. So how do we actually store the data on the physical media itself? When we're talking about a physical file system, we're looking at NTFS, RISE-RFS, ext1, 2, 3, or 4. We're looking at FAT, FAT32, FAT16. We're looking at all of those different things. The S3 file system from Amazon. All of those are physical file systems. But before we can look at that, we have to ask ourselves, what are we actually going to store persistently on the disk, and what do we not need to store persistently? Well, think about what we need to do. Obviously, I want the file to be persistent, and I want the metadata for the file to be persistent, and I need the directories persistent as well, because that's how I'm going to resolve the names of each of my files in inode. All of that needs to persist. But do I need the process's open file table to persist? If I'm shutting the computer down, it doesn't even make sense to have that anymore, because the computer is closed, the process is closed. If the process is dead, it can't own anything. If you are dead, you don't own anything. Yes, somebody could say, oh, that's my dead great aunts. Yeah, but they're dead, so they don't own anything. It's yours now if you want it. Sorry, I'm subconsciously making fun of my husband who has like his dead great uncle's long johns or something. I'm trying to throw them out for decades. I already did. Alright, so there's lots of things like that. There are structures inside of the kernel and inside of processes that don't need to stick around when they die. And those don't need to persist. Now, it's kind of a gray area on a modern machine, because if you think about the different levels of hibernation and sleep, there are machines that almost completely power off, and yet when you open them back up again, they continue at the same state that you shut them down in. And if you have a system like that, then some of those structures may actually be stored temporarily on the disk. It really depends on how that hibernate or sleep is implemented. For the purposes of this course, we're going to pretend such things don't exist. And then if you want to play around with it in real life, you're welcome to do so. All right, so we are going to show you first a file system that is based off of the old ext1, ext2 inode style file system. And to show it to you, we need to give you a disk. For the purposes of drawing the disk actually on the slide, our disk is going to store 256 kilobytes of data. That's smaller than the first hard drive I ever had. The first hard drive I ever had only stored 5 megabytes, but that's still bigger than that. So, with our 256 kilobyte disk, we have 512 byte sectors. That is actually a fairly standard sector size. But the one thing we realized is that if I tried to access this disk by sector, and I have on-demand paging, then each time I try to read or write a page to disk, instead of doing one I/O operation, I might end up doing 8. And as you know, if it's not sequential I/O on a physical disk, you're going to be paying out the nose for it. So, instead of doing sector-based reads and writes, because that is what the disk supports, we are going to group consecutive sectors together into blocks. And our physical file system, instead of doing sector reads and writes and sector addressing, is going to do block reads and writes and block-based addressing. And we are going to take 8 sectors and turn them into a block. So each block is 4 kilobytes, and that's super convenient because that's also the size of the page. And now if I want to do on-demand paging, every time I need to grab a file or a page from disk, it's one I/O operation instead of 8. So that's convenient. Now, what this means is that if I need to write 1 byte to a file, I have to read the entire block that contains that 1 byte into RAM, and then I make the change in RAM to that 1 byte, and I write the entire block back to disk. You absolutely cannot read or write a partial block from the disk. Even if you want a single bit from it, you have to read or write the entire thing. And that is not just because of the physical file system, it is because the disk itself can't do anything smaller than a sector read or write. All right, so because we're using 4 kilobyte blocks, we have 64 blocks on my disk. All right, so here's what my disk looks like then. See, this is why we have a small disk, so we can actually draw it and you can see it. So, 64 blocks on the disk. What am I actually going to use these 64 blocks for? Well, I'm going to reserve 8 of them for this particular disk to store some information about the file system that I need to actually retrieve the files and so on and so forth. Which leaves me with 56 blocks left to store file data. Now, because there are 56 blocks, and well, here's another interesting thing about files. You cannot have 2 files share a block, which means that with 56 data blocks, I can only have up to 56 non-empty files. And you might be thinking, isn't that restrictive? Sure, but your disk is 256 kilobytes. Why do you have 56 files in a 256 kilobyte disk? That doesn't make any damn sense. It's fine. We're not going to run out. All right. So the last 56 blocks are reserved for file data, and we are not sharing blocks between files. That becomes a bit of a management nightmare. Not saying it can't be done, I'm just saying it's a pain. All right. So we're going to now talk about the first 8 blocks, because those are actually the interesting blocks for our file system. So first off, if you're wondering what is this VSFS, that's actually the name of our toy file system here. Very simple file system. It's inode based, which means it's very similar to ext1 and ext2. All right. So we need a place to store the metadata for the file that tells me where can I find the file on the actual physical disk. Now when we store a file on a disk, we don't actually store it as a contiguous chunk. My file needs 10 gigabytes. Give me 10 gigabytes of contiguous blocks. Don't do that. Yes, it is good for the disk. It's good for the disk because then all of my I/O operations would be sequential, and that would be great. But here's the problem. I don't have just one file on the disk. I've got like 100,000 of them. And the problem is I end up with external fragmentation of the disk, and I end up with space on my disk that I can never use. Because we don't want that external fragmentation problem happening, we actually subdivide every single file into blocks. Kind of like paging. And now what we need is a magical way to keep track of where are all of the blocks that are stored in this file. What are all of the blocks that this file is using? Where can I find them? And I need a place to store the metadata in order to actually find them. And where we are going to store that is in this 5-block chunk called the inode array. Now it's not just keeping track of where the file data blocks are, and we'll talk more about that in greater detail later. This inode array actually contains, in this case, I think it is 80 inodes. And inside each of those inodes, what we actually have is information about each file. So each inode contains the metadata for one file. You can't have 2 files share an inode. It's one inode per file. And it contains things like creation time, modification time, size in bytes, size on disk, so on and so forth. All of the metadata, including where do I find my data, is contained in this inode. And our inodes on this file system are 256 bytes in size, which is why we get 80 of them out of this. And what's really interesting about that is that, you know that I number? Guess what the I number is? The I number is your inode index in that array, which is super, super useful. It means that once we get your I number, it's a constant time lookup in the inode array to get your metadata. That's great. I don't have to do a string lookup. I don't have to search a linked list. It's awesome. So inode arrays, that I number is actually the index of your inodes. So that's really cool. We'll talk more about the inodes in a few minutes. All right. So what about some of these other blocks? We have one block called the inode bitmap and one block called the data block bitmap. If you want to create a new file, there are a fixed number of inodes on the disk. The array of inodes is a fixed size. Yes, that means there is a fixed maximum number of files you can have on a disk. And you might think that is limiting. My disk here has an inode array that fits 80 files, 80 inodes, but I only have 56 data blocks, which means I can technically only have 56 non-empty files. So you're telling me that you have that many empty files? Probably not.
How there are 80 inodes?
So each block is 4 kilobytes. Each inode is 256 bytes. So 5 kilobytes times, or 4 kilobytes times 5 blocks divided by 256 gives you 80. Unless our math has been wrong for the last 20 years. All right, so there's a fixed number of inodes in the inode array, and that doesn't change. What's interesting is, and like I said, you might be thinking that that's very restrictive, but on this little tiny disk here, we could have up to 80 files. But we can't even have 80 non-empty files, so we're not going to run out. Nobody has 300,000 million empty files on their disk. Unless you're this guy here who tries to do it for fun. All right. So it's not a problem. But when you want to create a new file, you need to find one of those inodes that's not in use. How do you do that? What you could do is read the inode array into RAM and iterate through it. In use? No. Yep. Oh, this one, number 57. That's not in use. Okay, I need to use that. And on our tiny disk, that's not a big deal. Who cares about reading 20 kilobytes from the disk? It's sequential, big deal. All right, I have 14 terabyte disks at home. How big do you think the inode array is on that? Is the inode array, is it like a gigabyte in size? Because I would not be surprised if that was the case. So you're telling me every time I create a file, I have to read a whole gigabyte into RAM and iterate through it? That don't make any sense. And this is what the inode bitmap is for. The inode bitmap is a block or several blocks, depending on the size of your disk and the number of inodes you have, of data where each bit corresponds to one inode. If the bit is 0, the inode is free. And if the bit is 1, the inode is in use. So if I want to find a new inode or a free inode to use, instead of reading in the whole array, I read in the significantly smaller inode bitmap. And in this case, we have one block for it. And I simply go bit by bit. I still have to iterate, but I have less of a read and a write operation. I find a free one, I take it, and I write the updated bitmap back. Now what's interesting is that one block can map to 32,000 inodes. I've only got 80. So you can see that we can actually have bitmaps that are significantly smaller than the actual inode array itself. So it's a really convenient way of doing it. Now some people also use lists inside of there, but I think like a free list. But I kind of like this approach a little bit better. All right. Now similarly speaking, once I've got a free inode and I actually want to start writing data to the disk, I need to find some data blocks on the disk that are free. I have two options. I can read in every data block of the disk and check if it's free or not. How would I know? Because when we delete something, we don't exactly zero it out. We just kind of leave the data there and hope it gets overwritten. So it's either going to be really, really slow process to read in every data block and check it, or we won't even be able to determine whether it's in use or not. You know what? There's an easier way to do this. Why don't we just use the same strategy of having a bitmap where each bit in the bitmap corresponds to one data block. 0, free, 1, in use. I need 10 data blocks. I read the data bitmap in, I find 10 bits that are not used, and I take them. Write it back. So those are convenient structures we are using to identify free inodes and to identify free data blocks. Now, when you are deleting a file, it's not just about removing all of the hard links. What we also have to do as part of deleting the file is we have to read in the inode bitmap and the data node bitmap, and we have to mark all of the blocks that were used by that particular file as free. Otherwise, they can't be reused. You can almost think of those two bitmaps as actually being the memory management for this physical file system. All right. Any questions about that? All right. We have one last block that we're calling the super block. I suppose if you're a DC fan. I'm assuming the creator of these slides was. Alright. So what is the super block? Well, when you plug a disk into a computer and the kernel registers that disk, there's some basic information that the kernel of the operating system needs to know in order to figure out how to interface with the physical file system installed on that disk. For example, I need to know how big the disk is. I need to know how many inodes are in the inode array. I need to know where the inode array begins. I need to know how many data blocks there are. I need to know the size of the data blocks. I need to know the position of the inode bitmap, and I need to know the position of the data block bitmap. All of that information about how to interface with this particular physical file system is found in the super block. And when you mount the file system, part of that is going to be looking at the information in there so that the operating system actually knows how to talk to that physical file system. Of course, that will all be in the driver. So to take a little bit of a closer look at the first 8 blocks, you've got the super block used for the actual file system information. And then we've got one block dedicated to the inode bitmap, one block dedicated to the data block bitmap, and then 5 blocks which make up our 80 inode array. That's it. It's not too bad. Now obviously this is for a 256 kilobyte disk. If this was a 5 megabyte disk, we'd probably have a bigger inode array. We'd probably we'd obviously have more data blocks. This is going to scale based on the size of the disk. I would, however, tell you that certain file systems do have a file number maximum. So there is a maximum number of files that you can have under certain physical file systems. And if you're curious, Wikipedia will tell you all about it. And yes, some entries on Wikipedia are right. All right. So let's look at those inodes in a little greater detail, because they're kind of interesting. So first off, if we're looking at an inode, I said it contains 2 primary things. It contains all of the metadata for the file, but it also has to contain some mechanism to help you find where all of the data blocks of the file are. Except, keep in mind that the inode itself is a fixed size. It's only 256 bytes in this file system. So that's going to be particularly restrictive. So it does contain a lot of parameters. It contains all of the metadata. So we'll know things like the type of the file. Is this a binary file? Is this an ASCII file? Is this an image file? What is the file type? We'll also keep the permissions because it's very important to know who has permission to read, write, and execute this file, and that comes into play later. We also need to know the file length. Now, there's some interesting things about file length. There's the actual number of bytes occupied by the file. And then there's the file size on disk. And those are 2 very, very, very different numbers. And there's a reason for that. Part of the reason for that is because files are going to use the whole block. Even if I only need 1 byte, the file on disk actually occupied 4 kilobytes instead of just 1 byte. There's another reason for that, and that is that our page table occupies space as well. And we'll look at that in a minute. So, keep in mind that file size in number of bytes and file size on disk are often 2 very, very, very different numbers. And if you're copying from one file system to another file system, and you're like, oh, I'm in the FAT32 environment, and I'm going to copy it to this 512 megabyte ext4 USB key, And it's a 500 megabyte file here in FAT32. It should be fine over on that one. No, it won't be. There's not enough space for that. When you go from one file system to another, there's different file systems store the files differently. Some file systems need more space to store the file than others. That is why sometimes when you think, oh, it's 2 gigabytes, it'll fit, and it doesn't, that's part of it. You'll see that in a minute. Now, as part of this, we also keep track of what is the current byte position in the file. So what is the last byte? We will also keep track of things like when was the file created, and when was the file last read, and when was the file last modified. That's useful information because sometimes we like to know who's the most recent file, and so on and so forth. And then the last thing that we have as part of this is how we're going to keep track of all of the blocks that we have in the file. Now, instead of talking about this, I want to show you the picture. So obviously with 256 bytes, I can't store a huge page table here. You know that page tables are massive and, well, potentially big. So how do I store a potentially massive variable size page table in 256 bytes? Well, the answer is you don't. So what we're going to do instead is we will have sort of the root of this stored in the inode. And the body of it will be stored in the file data blocks, or in the data blocks of the disk. So in the inode, we have some number of direct pointers. A direct pointer is the address of a real file data block. The direct pointers usually start at byte 0 of the file, and they're the first, so that only small files will only use the direct pointers. That's a good one. Everybody's lost, crickets are heard. Alright, after having some number of direct pointers, maybe that's not enough for you. Maybe your file is bigger. We have some number of what's known as a single indirect pointer. It is a pointer to a block of pointers to real file data. The block of pointers is not a part of the inode. The block of pointers occupies a data block on the disk. If that's still not enough space for you, we have the double indirect pointer, which is a pointer in the inode to a block of pointers to file data. 2 levels of indirection. All of those blocks of pointers occupy data blocks. They are not in the inode. Yeah.
When I'm actually in my list of inodes, how do I know whether it's a single or double or like a triple?
The format is fixed.
Okay.
So it's like the inode will actually, the inode specification will say you have 9 direct at these byte positions here. You have 1 single indirect, it is here. You have 1 double indirect, it is here. So that is actually part of the inode spec.
So if I have lots of really big files or lots of very small files?
All inodes have the same thing. And if you are not using one of those indirect pointers, it's simply null.
Okay.
Yeah, so you just mark it as null. But combined with the fact that we keep track of the actual file size, we can usually figure out very, very easily which ones we are using and not. All right, now if the double indirect isn't enough, we have a triple. Okay.
So, is the reason that 16 gigabyte USB says it has 14 gigabytes in the computer because that's still all metadata?
It depends on the processor. But in a lot of file systems, the amount of space that's available is usually provided as the size of the disk. Now remember, some manufacturers will give it to you as a power of 10 instead of proper powers of 2. And then it usually sets aside some amount of data for the actual metadata of the file system, like the inodes or whatever it is. And yeah, what's left is what is for you. And so you get a subset. That value depends on the file system. Alright. So as I said, if you are outer space with doubles, then we have triples, which is a pointer to a block of pointers, to a block of pointers, to a block of pointers to file data. And we could theoretically, if we knew we were going to have super big files, we could have a quadruple pointer and a quintuple pointer. Please don't do that, because it's going to get really messy. Was there a question at the back?
Can you change the file system on an external drive?
Can you change the file system on an external drive? Absolutely. That's what formatting means. But you might want to clear your data off first. Yeah, so if you're in Windows, Partition Magic's a pretty great tool. And clean the data off. Partition, you can change to whatever file system you want.
So format doesn't change. So if you format, what do you do all the data so that you can take like just sort of data that's stored where the location?
So a quick format, scramble, a quick format to the same file system would just take the inode array, the inode bitmap, and the data block bitmap, assuming it was an inode style file system, and mark everything as free. Doesn't actually delete any data at all. If you were changing the file system or doing a low-level format, then it would actually scrub the disk and put down things clean again. For that. Linux also has formatting tools too. But yeah, you can change the file system of things to whatever you want. There's a lot of file systems you should probably avoid. Yeah.
Why does doing one pass format on a hard drive not clear all the data?
Like the quick format?
Or just like if you do a full format, but then you only do one pass through?
On like a physical disk?
Yeah.
So it has to do with the properties of the actual ferromagnetic material that's actually on the disk. My understanding is applying the current to it once isn't enough to completely change the magnetic field, such that it actually, I think it's 7 times you have to overwrite in order to make it so the previous data can't be found. I don't understand the physics behind that. That's the practice. I've never actually read the physics on that. Yeah.
Is it like if I erase something that you can sort of still see what was there before?
I mean, you could kind of think of it that way, yeah.
Okay.
All right, let's get back to inodes though. All right. So what you can see here is we now have a means of storing pointers to all of our file data outside of the inode. So the roots of this are all stored inside of the inode, and then all of the internal nodes are stored in data blocks of their own. Now, our particular file system, I think it has 12 direct pointers, 1 single, 1 double, and 1 triple. And that's actually going to give us a pretty big file. Bigger than we can actually store on this disk, or even 100 of these disks. Now, some other interesting things. So if you are not, so let's say you have a really small file, then you only use the direct. You only ever go to an indirect if you need it. And you only go to a double indirect if you need it. Otherwise, those pointers should be null, and there will be no blocks allocated. We only allocate these eternal block nodes if we need them. If we don't need them, don't make them. But as you can imagine, look at this file now. In addition to having all of these actual file data blocks, look at all the extra data blocks it's using to actually store the pointers to its data blocks. So you want a good little problem to do? Calculate for a maximum sized file in this very simple file system, how much data is required to store all of the indirect pointer blocks. There's a good sample problem for it. Yeah.
If I do allocate an indirect pointer block, is it like the page tables where I have to like all of it are going to be pointers, something more?
So if you need to use a single indirect pointer, and it's the first time you've ever used one, you will need to get a data block to store those indirect pointers, but you will only use the first entry in it. And all of the other entries should be set to null. Yeah. So any of the pointers you are not using in an indirect block should be set to null. But they still need to be. All right. So now we can actually do some calculations based on this to figure out how big of a file can we actually store on a very simple file system. So what we note is that we are going to make the assumption that our data blocks are going to use 4 bytes for an address, which means that we're using 32-bit addresses, which means we can address 2 to the power of 32 blocks. So our maximum disk size is 16 terabytes. My biggest disk size is 14, so it's pretty big, pretty good. All right. So what we see now is we start by trying to figure out what is the biggest file we can have. We're going to start by looking at how much space do I get from the direct pointers. So I'm going to put this up just a little bit so we can do the math on the board instead. That's, give some light. So to calculate how much memory is accessible from the direct pointers, you take the number of direct pointers and you multiply it by the block size. So in this particular example, we have 12 direct pointers. Each of them points to a block that is 4 kilobytes in size, which means using direct pointers alone, my file size could be 48 kilobytes. All right. Now that's good for maybe a text file or a code file. I don't know the last time I had an image file this small. I have image files on my computer that are 5 gigabytes each. They're huge. Photoshop hates opening them, obviously. All right, so that's not enough space for you. So you need to use a single indirect. So let's ignore the existence of the direct and let's calculate how much data can I access from a single indirect pointer. In order to do this, you need to figure out how many pointers fit in a block. So the number of pointers in a block is equal to the block size divided by the pointer size. Well, my block size here is 4 kilobytes, and my pointer size is 4 bytes. Well, what's 4,096 divided by 4? You should get something that looks like 1,024. So there are 1,024 pointers in these blocks. All right. Now I can calculate how much memory is accessed from the single indirect pointers. So it's the number of single indirect pointers. This is the number of single indirect pointers in the inode multiplied by the number of pointers in a block multiplied by the block size. So in this example, we have one single indirect pointer in the inode. There are 1,024 pointers in the block times 4 kilobytes per block. So that works out to be about 4 megabytes. All right, great. So I can have an image file from a Nokia cell phone. Okay. That doesn't work for my nice Canon camera. I need more space. I can't watch anything on this. Not even a real media file will fit. Okay. How much space can we get from a double indirect? Well, from the double, you get the number of double pointers, and that's in the inode, multiplied by the number of pointers in the block squared, because it's a pointer to a block of pointers to a block of pointers. Squared now times block size. So in our example here, we have one double indirect pointer times 1024 squared times 4 kilobytes. So this one was roughly 4 megabytes. This one is about 4 gigabytes. I can now download a really crappy version of Avengers. I'm sorry, I don't accept anything on my home that is less than 4K HDR, so. All right. So it's still not enough for me. We still have one triple left. Can you figure out the pattern here? It's going to be the number of triple pointers in the inode multiplied by the number of pointers in the block to the power of 3, because it's a triple, multiplied by the block size, and that gives me access to 4 terabytes. And then my total file size is the sum of all of these. So it's the amount we can access from the direct, plus the single, plus the double, plus the triple. We end up with a file that is over 4.4 terabytes and 4 gigabytes in size. I'd like to point out that the disk here is only 256 kilobytes. And yet from this one 256 byte inode, look at the size of the file I get. Now, the downside. Yeah. How much extra space do I need to store all these pointer blocks for this 4 terabyte file? So that's the thing I think you should try to calculate at home, is in a maximum file size, how much data is going to be used for the data blocks, or for the pointer blocks, on top of the file. And if you're wondering why is file size on disk and file size in reality 2 different things, look at all these extra pointer blocks we're using. And by the way, it is a lot. It is a lot of extra space. But if you're a 4 terabyte file, 4 gigabytes is like an ant under your foot. We don't really care. All right. Any questions about this? All right. So that's our file system. How do I actually do things on it now? Obviously, I'm going to want to do things like read and write. Okay, let's try that then. So, suppose I want to read from the file foo_bar. What do I need to do? Well, first, in order to open or read from the file, I need to open it. That means I need to get the I number for file foo_bar, which means I need to traverse the namespace tree and find the I number for file foo_bar. So I start at the root directory. Now, as part of the supernode, I actually am advertising what the I number is for my root. And on most systems, it's going to be 2, not 0 or 1. And so I know the I number of my root. And so I am going to read from my disk root's inode. Yeah.
Why don't we use 0 or 1?
On a lot of file systems, we actually use some file inodes to keep track of bad blocks on the disk. So when you have something like an SSD, which can have certain sectors wear down before certain blocks wear down before others, or that kind of behavior can actually happen on a traditional disk as well. You can have a bad sector where the material's damaged, and instead of throwing the disk away, the file system just says, hey, these are bad. And so sometimes we use some of those earlier inodes to actually keep track of that. Hence root is usually around 2. Not always. So. The supernode will tell you. So I'm going to read in the inode for root. When I read in the inode for root, I'm reading root's inode because I need to read root's data. Inside of root's data is the mapping for food. So I need to read root's inode to get the pointer to food or to root's data. So I read in root's inode, that gives me the pointer to root's data. And then I read root's data in. And inside of root's data, I will find the mapping from foo to an I number. And so I read in now foo's inode. And I'm looking in for foo directory because I want to find bar. So I get foo's inode to give me the pointer to foo's data. So now I can read in foo's data. And inside of foo's data, I will find the I number for bar. And now the part that surprises most people on an open operation, we also read in bar's inode. There's a few reasons for this. Well, do you have permission to open your friend's assignment? Can I just go on the CS servers and open files in your directory? I actually don't know that for me. But you guys can do it to each other. There are permissions. Because there are permissions, when we are opening a file, we need to make sure that we have the correct permissions for whatever we have opened this file for, whether we are opening it for reading, opening it for writing, opening it for both. We need to make sure that the user that has made that request has those permissions. In order to discover whether they have those permissions or not, we need to read in var's inode to get them from it. We are also, as part of open, now that we have the I number, we are going to create the file descriptor in the processes descriptor table. We will set the current position in the file to 0, and we update the kernel's list of open files to indicate foobar has been opened by another process. Yeah.
How would you know that bar is under the folder foo? Like, what if there are a bunch of folders and you don't know their bar is under?
Well, the path has to be specific. And if the path you provide isn't correct, then it throws an error. If you're trying to, let's say you're on a Linux system and you need to move to a specific directory. If you give it anything other than the correct path, will it work? Same thing. You must give a correct path. All of this just to open the file. You ever wonder why your disk light is sitting there blinking like a crazy person? To open this very basic file, I had to do 5 disk IOs. 5 disk IOs. I haven't even read a single byte of this file's data yet. It's kind of crazy. All right. Now what I'd like to do is, instead of going on to actually reading from the file, I'd like to give you a handout that's going to approach this from the other side. So this is the low level, what's going on. I have higher level here. If I can find it in my box. By the way, this one's posted to Piazza as well. They're all posted now. So what we have is, we want you to actually write the pseudocode to do this path name translation that we just did right here. And we've given you all of the functions that exist, and you need to use them to try. So take the next 4 or 5 minutes and take a crack at it, and then I'll show you one possible solution for it. They probably are. Extra? You need more? How old is that? I don't even remember when. I'm trying to remember when I first seen that. That's the problem. I don't know exactly what you're talking about. What's that? No, it's old. That's been around for a while. There's for nefarious purposes. I don't know, there were a lot of servers back in the day when people was on it. And then I never really played my games, but we telnet into like web servers and issue commands directly. So I send and I actually went to the CS350 I telnet into the web server directly, and then I used to send email requests directly. I was trying to not validate the address. Just validate, just check. Now, obviously, Nelson does that. The protocol itself does not. I've noticed that I can send, I don't send email, just tell it what email I want to because I actually put out one yeah, and like HTTP doesn't check. That's it for the mail server. Welcome to the internet. They don't check anything. It was never designed for security. Never. I can use a DNS server to do a distributed DOS attack.
Like from like on the school or just isn't that illegal?
Yeah. So So for the record, there's lots and lots and lots of valid solutions to this. This is just one. So if you have something different, it doesn't mean it's wrong. So what we're doing here is, in this case, our root has I number 0, which is provided in the problem. So I'm going to set my initial I number to be 0. Now, what I'm going to do is that I'm going to iterate over each of the path components, looking them up in the directory we are already at. So we're starting in the root directory, and what I first do in this for loop is I check to make sure that the current I number is a directory. I can't look up a path component in something that is not a directory. So I validate the fact that the I number corresponds to a directory. If it doesn't, this is bad path, return invalid. If it is a directory, then I'm going to do a lookup inside of that directory of the next component of the path. And that's going to be my new I number. Now, it's entirely possible that it was a directory, but that directory doesn't contain that next component of the path. So it's possible these search returns a value less than 0. You can't have a negative I number. So if the I number returned is less than 0, we return invalid. This process continues until you're at the end. There are no more components. You should have the I number for the final file, and we leave the loop and we return the I number. That is one possible solution of many. And the reason why I like to show this particular example with this is there you see what's going on in the disk, and here's the code to actually perform the search itself. Now you don't see the inode lookups, but they're there. Yeah. Alright, settle down guys. I can't hear the question.
For J equals I, K was 1 to know instead of for I equals
Alright, so I'm going to leave it here for today. We will finish this section on file systems on Thursday. We will also look at virtual machines as well.